Okay guys, this is the last video on solids of revolution. I think 5 is enough. This one has to do specifically with vertical axes. So let's go ahead and get started. Again, let's go ahead and identify the equations that we're dealing with. I can't say functions because one of them is certainly not a function. This right here is, of course, y is equal to root x. Okay, that's the blue one. This sideways parabola, let's see if I can actually follow that line. That sideways parabola is that one right there. And this linear, okay, is negative x plus 2. Now let's go ahead and actually take a region and spin it around the y-axis. We'll move beyond just the y-axis, but I think it's a good place to start. Let's actually take, let's take this region right here and spin it around. Okay, I think that's a good one right there. And we'll actually take that region and we'll spin it around this axis. Now, when we do that, we have to adjust for the fact that our cross sections are now going to be this way, right? Our little rectangles are going to be this way, the ones that are spinning around and creating those washers, okay? Which means that their width is no longer dx, their width is now dy. So I need not only to have dy as my differential, I need my integrand to be in terms of y, and I need my limits of integration to be in terms of y as well. Now I used Grapher to do this, and I zoomed in, and when I zoom in it kind of messes up the scaling. But that point right there, where all three of them meet, is 1, 1. That can be numerically verified, but let's go ahead and just state it outright. Now, I recognize the fact that if I'm spinning it around the y-axis, the curve that is farthest away for the region that I'm entertaining is this red curve right here, which is this quadratic. It is already x in terms of y. The one that is nearest is this blue curve. It is actually written as a radical function, but for our purposes here, it can actually be restated as x is equal to y squared. So now I have both curves, x in terms of y, and I simply need to designate one as big R. Well, remember, big R has to do with what is farthest away from the axis of revolution. Now, I mean, and if we're dealing with the axis, we're dealing with something that is more positive minus more negative. And of course, more positive in terms of x is to the right. So this is our more positive curve. It is our big R, and therefore our big R has that form. Okay. Big R squared, and I, again, cannot emphasize how much I recommend actually writing out R squared, R squared, okay? Now, this is y squared. So R squared is equal to y to the fourth. Now, from here, it winds up being relatively simple. It is pi from 0 to 1, that was our limit of integration. It's fairly easy to see, knowing what you know of the curves and seeing it on the graph and having numerically verified it. And then we have 2y minus y squared minus y to the fourth, which is our small r squared, dy. And that is basically the revolution of this around the y-axis. Okay? Let's go ahead and do another one. Let's do that same region, but let's spin it around the x is equal to 1. Sound good? So let's go ahead and we'll spin it around, like I said, the x is equal to 1 line. X is equal to 1. Okay? And we're spinning it around there. Now, the limits of integration are still the same. It's the same region, okay? So if I wanted to, I could go ahead and just put in what I already know, 0 to 1. Now, I don't want to put my dy down here, even though I know it's going to be there, because I don't know how long the expression is going to be, so I'm just going to be patient. I recognize the fact that, I don't really remember what colors I used last time, but let's go ahead and use red for the radical function, which was y is equal to root x, but I already rewrote it as x is equal to y squared. And let's go ahead and use blue for that sideways parabola, that conic. And that is x is equal to 2y minus y squared. Now remember that it's always the more positive minus the more negative. And when you're dealing with radii, their expressions, it is always either function minus axis or axis minus function. Now here the axis is farther to the right than either one of my curves. Therefore the axis is more positive. Both of my radii are going to be axis minus function. Now my big R is going to be axis minus what? Well, it's going to be that red again, okay? Well, it's red again, but it's not the same curve as the red in the last one. It's going to be that red curve which is farthest away from the axis of revolution and is going to form the outside surface of that volume of revolution, okay? So it's 1 minus y squared, or when I square it, 1 minus y squared squared. My small r is going to be 1 minus 2y minus y squared, okay? And when I square it, I can go ahead and just, this winds up being 1 minus 2y plus y squared. And so I can put it in descending order, right, and square it. Now, I have big R, I have small r. They are both with respect to this right here, which is why they were axis minus equation. And so I have 1 minus y squared squared minus y squared minus 2y plus 1 squared dy, and that right there is going to be the integral that I use to find the volume of that revolution. Now, I could, if I wanted to, actually take this, and could I find that region revolved around the x-axis if I wanted? Sure. And in order to do so, I would just have to take this sideways parabola and break it apart into the two different radical functions that they imply, and I would have to, of course, use the negative, the lower radical function, the reflected radical function, in terms of x, in order to actually formulate that particular integral and spin it around the x-axis. And if we have a second, actually, let's go ahead and do that. Yeah, might as well. Okay. And this of course gives you a good idea of how to switch back and forth in terms of variables, whether you're switching from x to y or y to x. We're going to do this same one, and we're going to flip it around the x-axis. We'll use red again for this one. Actually, I remembered this time. And blue again for this one. Okay. Now, remember, like I said, we have to take x is equal to 2y minus y squared and turn it into the radical functions that it implies. Well, if I have y squared minus 2y, that should be equal to negative x, right? And if I wanted to complete the square, which I do, which probably is going to be the easiest way to deal with this, then I'm going to have y minus 1 is equal to plus or minus the square root of 1 minus x, or y is equal to 1 plus or minus the square root of 1 minus x. Okay? That was a very easy way to transform it just by completing the square. It was obvious that that was going to be the best way to do it because it was, y squared and 2y. Those coefficients make that very easy. But this is two different functions, okay? And I want the one on the bottom. So therefore, I'm going to deal with this one, the negative one, right? Okay, because if I actually put this in terms of transformations, notice that it is that, which is exactly what that blue one is. It's the radical function moved over to the right one, reflected about the y-axis, reflected about the x-axis, and moved up one, okay? That is my y. That is my blue, okay? So now that I have my red is already, y is equal to root x. And then my blue is this one down here. And of course, I see it in terms of its transformations here, but I'm going to use that version of it. It is still 0 to 1, even though it's on the x, because it just happens to go from 0, 0 to 1, 1, right? That's just a coincidence. So 0 to 1. And then I need to remember big R is going to be root x, right? Because I'm spinning it around here. And this is going to, as I flip it around the x-axis, this is going to be the outer surface of that surface of revolution. So r squared is x. Small r is 1 minus root 1 minus x. So r squared, and you just go ahead and plot that into a parenthesis. So I have x minus 1 minus the square root of 1 minus x squared dx. And that would be the volume of that region flipped around the x-axis, revolved around the x-axis. And all you had to do, and some of you are like, oh gosh, completing the square, is do this, okay? Not that huge of a deal. Let's go ahead and maybe do one more very, very quickly. Okay, let's go ahead and let's do this one up here. Let's do that region right there, caught between the linear, which we'll go ahead and put in red, and that quadratic, which we have in blue. Now notice that this is a different region, so the limits of integration are going to be a little bit different. The limits of integration are going to be 1 to 2. Okay? Now, notice that this was y is equal, and of course this can become y is equal to 2 minus x, which means it can become x is equal to 2 minus y. That is what is going to be necessary in order to pair it with this, okay? My red graph is here, right? Let's go ahead and circle it in red so it becomes very, very apparent. And of course this was the blue one, just by way of reminder. Okay, well, my r, if I'm flipping it around this axis, just the y-axis, my big R is the blue. The blue is the farthest one away. Is going to be 2y minus y squared. And so big R squared is just that expression squared. Small r is going to be 2 minus y, and small r squared is going to be 2 minus y squared. So my integral is pi 1 to 2 big R squared, 2y minus y squared squared, minus small r squared dy. Okay? Now, that's 5 videos on revolution of surface. I hope that that's sufficient to explain it all. I've tried to be as efficient as possible and not actually work out many of them, but basically show you again and again and again how to construct the integrals. And that actually is the most important, well, not the most important part, but that's the part that you should be learning in this particular section. The mechanics of antidifferentiation or integration you should already have down. But if you have any questions, if you have any more different scenarios that I didn't cover but your teacher did and have left you confused, please do feel free to email me, and I will try to attend to that just as soon as I possibly can. Be on the lookout for videos on volumes of solids of known cross sections, and also 6.5, which is average function value and the mean value theorem for integrals.